Okay, next example I'm going to go through is bolt preload analysis, and basically it's just going to take you through the creation on this simple example. You can work through this yourself as part of the tutorials, but I'll just expand on some of the details of it so we can try and understand them. I know myself, I've set these up in the past and then tried to do it again on my own real example, and it's all gone horribly wrong, and I've been totally confused as to why that may be. So hopefully we can shed a bit of light on that. And what's important to remember or to understand is how it works in terms of a preload in Genesis. And what we're going to do is we actually define a bolt preload subcase, and that's where we just simply apply the tensile force to our bolts, and then we reference that bolt preload subcase in our applied load case. Okay. Is it possible to change the legend scale in post results? I've just got a question that's just popped up there. Is that going back to one of my results? I'll just check that. I assume we're referring to this legend here, where you can just change it by doing options. Is that the question my attendee has asked? In which case you can change the scale very easily here. Good. Thank you, attendee. And then to change it back, as mentioned, you must have not paid attention at that moment, attendee. I won't name you. You double click on automatic to return that back to the automatic level. Good. Okay, so going back to the bolt preload, what happens is you have this preload case, and what it's going to do is in the preload case, Genesis is going to internally measure what the relative displacements of the two parts of the bolt are to achieve that preload, and then internally in the solver, when you apply the overall load case and include the preload, it's actually applying an enforced relative displacement of the two parts of the bolt. It's almost representing you torquing down the bolt and creating that change in thread engagement length that you've turned on the part. Okay, so we'll come back to this slide in a moment when we've set up the process and we've understood a little bit more about how it works. So with that, I shall open up my meetings are arriving. Bolt preload. Here we go. So here's our simple example. As mentioned, this is a tutorial you can work through yourself if you wish to do so. And what we've got is the way that the process will work inside Genesis is that it will automatically split the bolt into two discontinuous meshes, and then it'll place a bolt element, it's called, in the gap in between. So to do that, let me get back to there. We've just made our life a little bit easier for this tutorial and put the two halves of the bolt into separate groups. They're actually, as it stands at the moment, very much one continuous mesh. If I was to, for example, pick nodes at this end, or I should say not nodes, if I pick elements at this end and add connected, you'll see it connects all the way up. Now, just personally as well, I would tend to always have a nice hexa mesh for a bolt. That's just my preference for modeling. So what we're going to do is we're going to use a function inside Design Studio that allows us to create the bolt element for both of these. And then we'll be able to define our pretension. So first of all, we have to create a bolt group. So we go to New in Group Properties, and we'll choose our bolt holder. So we'll make them blue. And when we describe them as bolt elements, these are the interpolation elements that create the preload condition. So I can now go ahead and create those. And I can hop across to display. So to make my life easier, I'm just going to show these surfaces. Now, what becomes very important is which side of the bolt I'm looking at, and therefore where I'll apply my force eventually. So I've chosen, if you look at this, to show the bottom half of the bolt, and these are the bolt heads at the top. So if we now go create, we've got this function to create a bolt element from selected faces. And what we're able to do is work our way through choosing the group, and you basically pick the exposed surface where you want the bolt cross section to be applied. And this is a very, very important option here, which is to apply whether I've chosen the bottom or the top. And in this case, this is the bottom of the bolt. So I've chosen bottom. I choose finish. And you can see that what looks like a rigid spider has been created. It's actually this bolt interpolation element. And I now have a bolt control grid where I can apply my preload. I'll repeat that step on this one. Notice I click the select none option, otherwise it'll create me a bolt across the two face selections. Choose bottom here, and I've got that. So they're now both done. I have my bolts, and what you can see, if you investigate what has happened inside Design Studio, to zoom in a little bit here, if I go to identify grids and pick, you'll find there are now two grids. So it's detached the two meshes together, apart from each other, and allowed us to study that. Okay, so our next step, now I've got my bolt element, is I can define my preload. And the way to do that is to go to a static load, and I'll just simply go preload. It's just a force that we're applying at this moment. And what we need to do is we need to pick our two control grids to apply our forces to. And the way we want to define the force is it needs to be defined in a direction that goes from the bottom to the top of the bolt. Now, bearing in mind that we've given it that convention that I chose to call those elements bottom when I made the selection. So bottom to top in this case is going up the positive Z direction. So if I want to put 5 kilonewtons of preload, I can apply that to these center nodes, like so. Okay. Like so. I almost tricked myself up there with a little coordinate system. Good. So now they're applied. You can see they're in place. I can choose to define my preload subcase. So here I can do preload. It's again just a static load case. I can't spell. I'll fix the structure, the model as normal, and apply my preload. Just do there, contact pressure and stress if we want to look at that. So that's my preload condition. Now what I want to be able to do next is I want to incorporate that into my applied load case. So for that, what I need to do is create a copy of our initial pressure loading here. And preload. So I've got my cases and contacts all as expected. So this is something that's been predefined in this tutorial already. I won't go through the setup of that. And then what I can do is I can choose to select my preload subcase as a preload condition to be including. Okay. So what I'm also going to do is just do post both here. I'm going to request the reaction forces, and we'll come to that in a moment as to explain why. So now this particular load case is the pressure case without the preload included. Now actually, without preload being defined, that will present itself with some numerical problems, because this interpolation element I've put in place when I don't use preload means that actually the two parts of the bolt are disconnected. So I'm just going to simply delete that for this demonstration case and run these models. My first live demo error has quite clearly not worked. So what have I done wrong? My own stupidity. In the preload case, I didn't put my contact in, so it's trying to apply a preload with no contact definitions. So I think I at least understand my error there, so we can do that. Let's see if it's as simple as that. Of course, I'd like to say I did that on purpose to make sure I taught you and you're all paying attention. Better. Good. Okay, great. So we can take a look at that. Now, I've already got the results, so just to show you here, so this is my, no, just a moment, here we go, load case 3, yep. So here is the loading of the pressurized vessel without any preload. You see the surfaces in this particular case are in fact pulling apart. And if we now look at the displacements for the preload case, remember that the displacements here are scaled by 478, so grossly exaggerated. You can see for this case, this is the stress being applied as a preload, the contact as it compresses. And then here we've got our preload and pressure applied together, so you can see the part is lifting up. Now, what's useful to understand is to confirm the preload, or I should say the tension in the bolt when the load is applied. So I've realized there's one output I need to just rerun quickly for you all. Reaction force in that bolt preload case as well. Just resolve that. Great. Now, as you'll notice, I've imported the results twice, so if you're not aware of it, each time you import results into Design Studio, it puts them into this Manage Results Dataset pool here. And so you can see I've got all the results once, and then I've got the previous import here. And these at the top were the before I put the preload in. So I'm going to delete that set of results. We don't want them. What I wanted to show you was the reaction forces here. Yes. Now I'm getting myself into a mix. There we go. So this is the bolt control grid. If you notice here, we've got a load of 4,236, and that's the tensile force in the bolt once we have a 5 kilonewton preload applied, and then the pressure applied as well. So I will need to do one more run to demonstrate it a bit more clearly. I would skip through it, but I think it's important. This topic is covered properly. So if I do preload only, as mentioned at the start of this preload discussion, the load case of a preload application is applying the force to the bolt. So we know that the tensile force is 5 kilonewtons. It's load driven. What we want to do is trust that's the case, and I want to prove that out here with this solve. So what I'm going to do in this preload only case is I'm not going to apply any other external force, but I'm going to reference the bolt preload case. So it's going to just simply torque down those bolts as a solve. So we'll pursue this last one. So we should have now a third case. There it is, number 5. And so this one that's solving now is simply applying the bolt preload that we calculated as a force and reapplying it as an enforced displacement, which is what happens when it gets included in a subcase. So if we take a look at this, what you see now is we've got the reaction force at that bolt control grid is at 5,000 newtons. A little high at 5,006. Obviously some convergence in the contact going on there. But you can see that's our bolt preload. So what it's telling us is actually by applying the pressure load to this vessel, the bolt preload is being overcome and it's reduced it down to 4.2 kilonewtons as an output. So it's a useful thing to measure often when you're looking at such cases in the real world, is knowing what's happening to the bolt and its cross section. Okay, so just some pointers to recap with regards to bolt preload. As mentioned, this definition of the bottom and the top is really very important. So when you define it using the interface that I demonstrated, you make sure if you're picking the bottom set of grids, then you say so on the interface. So that's there. And once I've done that, that's the order that they are around. You then apply the force in the positive direction for the bolt. If you do have something that's, as is often the case, not in a nice pure Cartesian coordinate system, then what you need to do is you need to reference, create and reference a local coordinate system that aligns to the bolt axes. And this control grid, after it's been created via the interface, is you need to modify that control grid so that its output coordinate system is referencing that aligned coordinate system that you have. If that's not at all clear, I won't spend the time setting it up, but I can just show you one that's been set up accordingly. So this model, if I do it in a standard view, you'll see it's all at a strange angle, and all we've done is created a coordinate system that we can see here is aligning along the axes in Z. And so we can do that very easily in the process. If I just look at my control grids here, these ones here, in the grid selection, with them selected, I can just modify a grid and I can change its output coordinate system via the grids menu to my local one here. And that way it all works in that direction. And similarly, the static load that we have should be applied along the axes. And here again, you can do that by referencing the local coordinate system when you apply your force. And that's all done. Okay, that is bolt preloading Done. Good. So that concludes our work on statics. Before I move on to buckling, I have a question that's popped up. You have to model the bolt in 2 sections. Yeah, so it splits it up for you. I see the question there. So when you mesh the bolt that we just saw, if I go to any of these, you just simply mesh that as one. If you've meshed that as one single part, in here in this example, it's been split into 2 groups, so it's very easy as a tutorial to hide them. But equally, if they are, for example, if I do this, and I put them into this group. So say, for example, I only had that there, then the process of creating the data is exactly the same. What I do here is I simply show hide elements, and I can just choose where I want my section to be, hide the elements, and then I pick these faces here, again on the bottom surface, and it will do the splitting automatically. So it will create new grids, create the bolt element, and connect it all together in the way we want it to. Okay, I hope that answers your question. As mentioned, I have a certain obsessive compulsive disorder with meshing that I like to have that as a nice extruded hex mesh. It's a much better way to do it, but it will, as is demonstrated here, work in either way. Good.